So this video is our introduction to the next unit, section 5.1, which is areas and distances. We're going to start looking a lot at area problems. To start out, what we're going to define by the area of a region, we're going to call that region S. We're going to say it's the area that's under the curve, in between our two vertical lines there, x equals a and x equals b, and then also the x-axis. So basically, we're chunking off some area under a function between two x values. And when we say under a function, we mean the area between the function and the x-axis. So the example we're going to look at to start is x squared. So you'll see as we work through the example, we'll be working with things being squared, and that's just because we're working with x squared. That won't be the same in every case. If we had x cubed, we'd do x cubed. If you had 2x plus 1, you would see things being multiplied by 2 and adding 1. We're just going to work with x squared, though, in this case. The technique we're going to use to find the area of this region is we are going to split it up into rectangles. Now, if you think about it, you can probably conclude that our area of this region has to be in between 0 and 1. It has to be greater than 0 because there's obviously some area there. And if you took the area of this square here, which is 1 by 1, we know that area is 1. And our area is clearly smaller than that. So we know that our area should be something in between 0 and 1. So we will split our region into some rectangles. Now the questions you will do will always tell you how many rectangles to split it into. So that's not something you're going to have to come up with on your own. So to start out, we're going to say, let's say we split our region into 4 rectangles of equal width. Well, because we are going from x values from 0 to 1, that length gets split up 4 ways, so each width now is just 1/4. So whatever the total width is of your region, divide it by the number of rectangles, and that will tell you how wide each section is. So our first section goes from 0 to 1/4, and then the next one from 1/4 to 1/2, and then from 1/2 to 3/4, and then 3/4 to 1. Now, you may be thinking, well, we said we were going to split it into rectangles, and those aren't rectangles. Well, this is just to show you where we're getting the base of those rectangles from. For our heights, there's a couple different methods that we can use to determine where the height of that rectangle should be. The first one we'll look at is approximating the height using what's called right-hand endpoints. What we mean by that is, in that first rectangle, the base of it goes from 0 to 1/4. The right-hand side of that rectangle is at 1/4. To determine the height of our rectangle, we will use whatever the height is at 1/4 when we're working with right-hand endpoints. In the next rectangle that goes from 1/4 to 1/2, the right-hand side of that rectangle is at 1/2. So we will use the y value at 1/2 to decide how high to draw that rectangle. Likewise, the next one from 1/2 to 3/4, we'll use the y value at 3/4 to determine the height. And from 3/4 to 1, we'll use the y value at 1 to determine the height. This now sets us up with 4 rectangles that we're just going to find the area of, add together, and that will be our approximation of our area under the curve. Well, a rectangle's area is base times height. Every one of those rectangles has a base of 1/4. So notice, written in black there, everything is 1/4 times something. Our height is just our y values. Remember, a y value is how much you're moving off of the x-axis. So our heights of our rectangles are the distances at 1/4, 1/2, 3/4, and 1 that we moved off of the x-axis. So therefore, in our first rectangle, f of 1/4, or in other words, our y value at 1/4, that will define what the height of our rectangle is. F of 1/2, our y value at 1/2 will define our height of our second rectangle, our third height, and our fourth height. And again, notice our base was 1/4 for each of them. Now, I purposely wrote this F notation to stress that the functions will change that we are working with. In this particular function, we're working with x squared. But whatever the function is, you will plug your x value into that particular function. So in this case, we will put 1/4 into x squared, and that's why we get the 1/4 squared below. We'll put 1/2 into x squared. That's why we get the 1/2 squared below, and so forth for the others. And again, because that's giving us the y value, that's giving us the height. We're really just doing base times height 4 times and adding them together. Well, when you add those all together, we get 15/32, which is about 1.46 or so. Now, is this approximation of our area under the curve an overestimate or an underestimate? Hopefully you're thinking an overestimate because we have sections in our rectangle that go outside of our region underneath our curve. So this would be an overestimate. So therefore we know our actual area is something less than that 0.46 or so. So I mentioned this is just one method that we could have chosen the heights. Well, this was using the right-hand endpoints of the rectangle. Another way will be using the left-hand endpoints. So the picture on the left, you see we're using right-hand endpoints like we just did. The other option would have been to use the left-hand endpoints. So in that first rectangle that had a base going from 0 to 1/4, if we use the left-hand endpoints, we're really using f of 0. And if in that second rectangle from 1/4 to 1/2, if we're using left-hand endpoints, we're using at 1/4. So notice we're using f of 1/4 for the height, and then f of 1/2, and then f of 3/4, because those are the left-hand endpoints of our 4 rectangles. Again, I show you the function notation because that will be true in every example we do. What's different is we're doing specifically the graph of x squared, so we'll plug those x values into x squared. We get 7/32, and that's about 0.21. Now, looking at the picture, the left-hand endpoint picture, think about, is this approximation an overestimate or an underestimate? Hopefully, you're noticing the gaps in the area under the curve and are thinking that this is an underestimate. The actual area underneath our curve should be something that is bigger than that. Well, what we've done is we've narrowed it down even more. We said initially we knew it had to be between 0 and 1. Now we know it's got to be somewhere between 0.21 and 0.46. Well, to get a better approximation, what if we split it into 8 rectangles instead of 4? Now again, you're not going to have to choose how many rectangles to split it into because you will be doing this type of process a bunch. The question will say, using 8 rectangles or using 4 rectangles. So if we're using 8 rectangles, that means we're jumping 1/8 for each width. And we'll use, when we have right-hand endpoints, we'll use f of 1/8, f of 2/8, f of 3/8, f of 4/8, and so forth, all the way up to f of 1. When we're using left-hand endpoints, we'll use f of 0, f of 1/8, f of 2/8, f of 3/8, all the way up to f of 7/8 for our heights. Now, when we do that, if we were to compute it just like we did before, we get 0.27 for our lower and 0.39 for our upper. So notice it's coming together. And in fact, if n is our number of rectangles, notice as our number of rectangles keeps increasing, our left-hand endpoint estimate and our right-hand endpoint estimate keep getting closer and closer and closer. Notice they appear to be approaching 1/3. So based on this, it looks like our actual area under the curve is 1/3. Well, we're going to show that algebraically in a second. What this is saying, remember, r sub n is just the area or the sum of the rectangles using right-hand endpoints. By saying as n approaches infinity, it says as your number of rectangles grows and grows and grows, or in other words, as those rectangles get infinitely skinny, our area or our rectangles, when we add them up, approaches 1/3. And it can also be shown the other way as well, that the left-hand rectangles are approaching 1/3. So let's think about this. If we draw in a bunch of rectangles, so we're going to say we draw in n rectangles. Well, when we had 4 rectangles, 1 divided by 4 was 1/4. So each jump for the width of the rectangles was 1/4. When we had 8 rectangles, we had 1/8. And the reason it was 1/8 is because our total width is 1, and it was split into 8 ways. Well, now we're going to say we have n rectangles. Okay, some integer number, positive integer number of rectangles. Well, if we have n rectangles, that means each jump is by 1/n. So the first rectangle, the base goes from 0 to 1/n. The next one goes from 1/n to 2/n. The next one from 2/n to 3/n, and so forth. So our heights, if we're using right-hand endpoints, our height of our first rectangle, the right-hand endpoint would be 1/n. So we'll be doing f of 1/n, which in this case is 1/n squared. The second rectangle, because that width went from 1/n to 2/n, the right-hand side is 2/n, so that's why we'll use 2/n squared for our second rectangle. And we keep going all the way to the last rectangle, which is n/n, which is the same as 1. Now, something we're going to use when in our proof that this sum actually is 1/3 is this formula 1, your textbook calls it. And again, you won't have to produce this or use this in a proof, but we're going to use it in the proof just to show you why it works, but you won't have to ever use it on your own. And what this is just a formula for the sum of some set of consecutive integers squared. So 1 squared plus 2 squared plus 3 squared plus 4 squared up to some number squared. So if you went up to 7 squared, then n would be 7. You can just plug in 7 in for n in your formula, and you would get what the sum is. So if we look, as our rectangles get infinitely large, it appears that it becomes a much better approximation of our actual area under the curve. So what our goal is going to be is to see as that number of rectangles approaches infinity, remember n was our number of rectangles, we want to see what number does our left-hand or right-hand endpoint sums approach. And we're going to show for the right-hand one that it's 1/3, and you could likewise show it for the left-hand one if you wanted, but we're just going to do it for the right hand. So, for our right hand, we had said that the width of each rectangle was 1/n. Our function we said we're working with was x squared. So our intervals that we have for rectangles, the first one goes from 0 to 1/n. And it doesn't matter if you do squared brackets or rounded brackets. I'm just using them to show the intervals. Next, from 1/n to 2/n. Next, from 2/n to 3/n. And that keeps going all the way to n minus 1/n, comma n/n. So n minus 1 is saying if we had 20 rectangles, it's going from 19/20 to 20/20. So to find r sub n, what that's saying is adding up all of your rectangles using heights being the right-hand endpoints. Every single rectangle will have a base of 1/n, and then a height of f of whatever the right-hand endpoint is. So the first one will be f of 1/n, plus a base of 1/n. The second one will be f of 2/n, because that's the right-hand endpoint in our second interval. And then we'll do plus 1/n of f of 3/n. And this will keep going all the way till 1 over n times f of our last right-hand endpoint, which is n over n. Okay? And we'll just put the plus dot, dot, dot in the middle there to show that it keeps going. Well, what we're going to do is we're going to neaten this up a little. We know our function's f squared. So what we really have is 1 over n times 1 over n squared plus 1 over n times 2 over n squared plus 1 over n times 3 over n squared plus dot, 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 dot. And the last one you'll have is 1 over n times n over n squared. Well, we're going to look and see what do we have in common that we could factor out. Every term has a 1 over n. And also, because everything has an n that will be squared on the bottom, each term also has a 1 over n squared. So we can pull out a 1 over n and a 1 over n squared. So the 1 over n is the part that's out in front of the parentheses. And after you square both top and bottom, because everything will have an n squared on the bottom, we can also factor out a 1 over n squared. Well, what that's going to leave us with is just our numerator squared. So we'll have 1 squared plus 2 squared plus 3 squared plus all the way up to n squared. Well, out front, this is just 1 over n cubed. And in the parentheses, there's that formula that you just copied down a second ago. The sum of our first n integers is just n times n plus 1 times 2n plus 1 all over 6. And again, that's coming from the formula you just copied down on the previous slide. Well, now we're just going to neaten this up. We can take one n away from both top and bottom. So that will give us n plus 1 times 2n plus 1 over 6n squared. And if we FOIL out the top, we'll get 2n squared plus n plus 2n plus 1. And when you combine your like terms, you'll get 2n squared plus 3n plus 1 over 6n squared. So what this is a formula that will give you the sum of your rectangles using right-hand endpoints for any number n of rectangles. So if n was 8, we'd just put in 8 here. If n was 12, we'd put in 12 here, and it would automatically give us the sum of our rectangles, which will approximate our area under the curve. Well, we saw in the previous slide that when n gets infinitely large, that's what will make our rectangle area approach the actual area, because it becomes a better and better approximation. Well, if we want n to get infinitely large, we're going to take the limit as n approaches infinity. So we'll look at the limit as n approaches infinity of 2n squared plus 3n plus 1 over 6n squared. Well, the easy way to evaluate this is, remember, when you approach infinity, that's like looking at a horizontal asymptote. Horizontal asymptotes are what happens when you go to the far right or far left. In this case, it's to the far right. Well, you saw in pre-calc and we saw in our graphing unit, horizontal asymptote of a rational function, when the degrees are the same, just look at the leading coefficients. So we have 2, 6, which is just 1/3. So we just showed algebraically, using our limits, that in fact, that right-hand endpoint sum of our rectangles, as n gets huge, is in fact going to approach 1/3. And you could show it with the left-hand one as well, but we're just going to show it with the right-hand one. So now let's look at the general region, and we'll apply that same principle. So we had that general region that we began with. If we split that into some number of rectangles, we're going to say we have n rectangles. So our first one will go from x0 to x1. Next one will go from x1 to x2, and so forth. x0, notice, is the same as where your interval starts, your a. And the last one, xn, is where your interval ends, b. So you can think of this as going from a to x1 and x sub n minus 1 to b. Well, you might be thinking, how do you find what x1, x2, x3 are, and so forth? Well, it all depends on your width. Let's say our width was 1/5, we'll say. And let's say a was 7. Well, then you'd go from 7 to 7 1/5. And then you'd go from 7 1/5 to 7 2/5. And so forth, and you'd keep going to whatever the end would be. So to find each of your x values, you're just adding your width onto your original value. So to find x1, you'll take your a, like we had said a was 7, and what if our width was 1/5? That would give us 7 1/5. Well, you'd add another fifth on to get to the next one, so that would give you 7 2/5. And that's just a specific example to help you see where it's coming from. So delta x we should write down. That is your width. And we are always going to find delta x by doing b minus a over n. B minus a is the endpoints of our interval. So that will tell us how long the total width of our interval is. And then n is our number of rectangles. So we're basically taking the entire width of our interval and splitting it up into an equal amount for each of our rectangles. And again, we'll use this in actual problems because it's going to be important to find the width because that'll be the base of each rectangle. Now, people always get confused with this notation. We're going to approximate with the ith strip. All that means is we're going to pick a random strip. So just pick a random rectangle. That's all the ith strip means. Well, we know delta x is the width, because that's the width for everything. Now, by saying f of xi, that's just saying the height of that random strip. So delta x is the base or the width for all of them, and the height will just be whatever the height is for that random strip at the random right-hand endpoint. And so there's just a representation of the sum. And we've talked about that before in the previous example. We can approximate that actual area by the sum of those rectangles. Here it's showing it with right-hand endpoints. And we talked about before, as our number of rectangles gets larger and larger, it becomes a better approximation for that actual area under the curve. So we just saw a second ago, we want to think of the limit as n approaches infinity. That means as our rectangles, the number of them gets really huge. Whatever that's approaching, that's the actual amount. Now notice the difference between right-hand endpoints and left-hand endpoints. Right-hand endpoints, because your first interval went from x0 to x1, remember x0 is the same as a, and then from x1 to x2, your first right-hand endpoint was x1, and then the next one was x2. But when you do left-hand endpoints, your first one will be the x0, that a, and then your second one will be x1. And likewise, your last one will be x sub n minus 1, comma xn. So if you're doing right-hand endpoints, your last right-hand endpoint is xn, which is the same as your b, your end of your interval. And x sub n minus 1 will be used when you're using left-hand endpoints. Now, because our rectangles are going to get infinitely skinny as the number of rectangles gets larger and larger. Once those rectangles get really, 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 really skinny, the difference between your left-hand endpoint and your right-hand endpoint is going to be inconsequential. So all they're saying on this slide is, once your rectangles get really skinny, we could really just pick any point that's in your interval, and that should give us an approximation of the height. Because as your rectangle gets super skinny, it doesn't matter if you pick the left-hand endpoint, the right-hand endpoint, or anything in between. It should be a very similar height because those rectangles are so skinny. So that's all this notation is meaning. Okay, and it usually throws people off a little bit, but that's all it's saying. When the rectangles get really, really skinny, you could, in your random rectangle, just pick any random point in the interval. It doesn't have to be a left hand or right hand. And you can see that here. These x stars, x1 star just means a random point in the first interval. X2 star means a random point in the second interval. And notice they're bouncing around, because as those rectangles get skinnier and skinnier, by picking a random point in there, it's not going to matter. They're going to be so skinny. So in general, what we're saying is we can do our width times our height for each of them. As n approaches infinity, we can use those random x values, not the lefts or rights. You could use lefts or rights, and they could be those, but they don't have to be. And this can be written in sigma notation. If we wanted to write this, so this would be the sum of our right-hand rectangles, because notice it's starting with f of x1 and ending with f of xn. This can be written in summation notation, because remember, you plug the bottom number in first, and that would give us f of x1 times delta x. And you'd keep going until you get to the last one, where we'd plug in f of x sub n times delta x. So notice these are going in for the i's, which is our subscript here. And that's just going in for 1, 2, and so forth. So it's just a different way of notating it, and it's a shorthand way of doing it. So we just saw our right-hand endpoint 1. The difference in our notation if we did left-hand endpoints is we would have to have an I minus 1. The reason we need that is when we plug in 1, we want to get back 0 for our first left-hand endpoint. Because remember, we start x0, x1, and then x1, comma x2. We want to get x0 and x1 as our first two. So when you plug in 1, 1 minus 1 is 0. And then when you plug in 2, 2 minus 1 is 1. So that gives us what we want for left-hand endpoints. And then the bottom one is just saying once those rectangles get big enough, you can pick a random point in there. Now, the ones that we will see to start out will ask us to do a left-hand endpoint and right-hand endpoint. People often get scared by all this notation. The actual problems you're going to have to do, it will say use 6 rectangles to approximate the area with right-hand endpoints, or use 6 rectangles to approximate the area with left-hand endpoints. All of this notation is to show you why we're doing it and where it is coming from. So here's just that sum of the integers that we did before, the sum of the first n integers. This is just a neater way that we could have written it. Instead of writing 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared, we could write it neatly like that. And you should get used to writing summations. You're going to see them a lot in your math career as you go forward, just because it's a shorthand way of writing it. And our last thing for today, just copy down these 3 formulas. Where we will see them is just when we're proving other things like we did today, we might need to use them in the proofs. Just like we did the sum of our squares written nicely, we'll want to have these down just so we can reference them quickly when we do our other ones. The first one is the sum of just n integers. And you saw something similar to that was on your reference sheet in trig. The second one is your sum of your cubes. And the last one is just saying, if you add a constant up a bunch of times, it's just the number of times you add the constant times the constant. So for example, if I do 7 plus 7 plus 7 plus 7, well, our constant we had was 7 times the number of times it showed up, which was 4. That's all that last one is saying. That's all for today's video. We'll see you next class, period.